All right, so good afternoon and welcome to everyone. This is the second annual 3-Minute Thesis Competition at UT Southwestern. We're really excited to be at Pegasus Park this year in this beautiful space, and thank you for crossing the highway to support your students. So I'm Priyanka, this is Lexus, and we are fourth year graduate students here and the organizers of 3-Minute Thesis and your hosts for this afternoon. So before we start, I want to thank all of our partners. So starting with the Graduate Careers Office, so Dr. Natalie Lundstein and Barbara Strom, thank you so much for all of your help. Yes, they've been huge support. We'd like to thank GSO for providing the prize money that we're going to be giving to the students today. And we'd also like to thank the Blackstone Launchpad for sponsoring the space and the video recordings that we're going to get. Yeah. And thanks to Pegasus Park for allowing us to use this conference room.
Yeah. So I'm supposed to say, before I even go into thanking the judges, that we have Blackstone swag at the back, so please pick it up. Natalie does not want it anymore. And she said you can grab 100 sunglasses if you want. But besides that, thank you to our judges who are here today. I've been talking to you through email, so I'm really glad you were able to come out and support our people today. Our judges are Dr. Joyce Repa. We have Dr. Stu Ravnik, Dr. Yuminchuk, Dr. Nick Conrad, and Dr. Edward Groh. And so thank you for supporting these students, and we're really excited to have you all out here today. One last thing before we really get into it, we have an audience favorite besides the first, second, and third prize that the judges will vote on. And so we'll have a QR code that's going to be on the presentation. You go and vote, and then we will have an audience favorite that we're going to give away at the end.
So we're going to get started with our first talk today. So Therese Cook is a fifth-year neuroscience student in Dr. Todd Roberts' lab. We asked all of the speakers to send us a one-liner of anything they wanted us to say about them, and Therese said that in her free time, she is an avid knitter, crocheter, and embroidery artist, and is addicted to buying craft supplies. So her talk today is entitled Baby Bird Babbles, What Songbirds Can Teach Us About FOXP1 Syndrome. So Therese.
Can I go up here? Okay. Just making sure I'm standing in roughly the right spot. So, would you believe me if I told you that I could implant an idea in your mind just by sending the right combination of vibrations through the air? It might sound like magic, but it's very real, and I'm actually doing it right now. As we speak, my brain is translating ideas into words, into sounds, into movements of my mouth that are causing waves of pressure to travel through the air to your ears, where your brain decodes them. In case it's still unclear, what I'm describing is language, and we as humans are experts at it. Not only that, but we learn language effortlessly as babies without any kind of instruction manual. At least that's the case for most people. Like with anything so amazing and so complicated, there's a lot of ways that language learning can go wrong. Today, I'll be talking to you specifically about FOXP1 syndrome, a disorder caused by a mutation in a single gene which causes people to have extreme difficulty speaking. We know that disrupting this gene causes language problems, but exactly what step in the process is affected remains poorly understood. To address this question, I and a group of awesome scientists from my lab decided to mimic FOXP1 syndrome in a bird called the zebrafinch. Like humans, zebrafinches learn their songs as babies by listening to adults. We can break zebrafinch song learning down into two main phases. In phase 1, baby birds must memorize the song of an adult bird that they want to copy. Then in phase 2, they practice making all different sounds until eventually they can perfectly replicate that example song. In our experiment, we let one group of birds memorize the adult songs like normal. Then we manipulated their brains to mimic FOXP1 syndrome to see what effect this would have on the subsequent practice stage. To our surprise, these birds actually learned to sing perfectly good songs, which tells us that FOXP1, at least in the part of the brain that we manipulated, isn't necessary for the refinement of vocalizations through practice. In a second experiment, we manipulated the birds' brains before they ever heard song. So now it's affecting both the memorization and the practice phases. Unlike the first group, these birds did not learn to sing. They still made sounds, but they were nothing like the example songs they were trying to copy. Overall, this tells us that FOXP1 is necessary for the formation of a song memory to guide subsequent vocal learning, but not for the practice and performance of song once that memory has already been formed. This gives us not only more insight into how these birds are learning to sing, but also into what aspects of language learning might be more affected in people with FOXP1 syndrome. And in the process, we take a baby bird-sized step forward to better understanding the magic that is human speech and language. Thank you.
Awesome. Thank you, Therese. Great talk. Next talk we have is Choshi Wang. Choshi is a fourth-year GD&D student in the Pingmu lab. He is a movie and game lover and says he is still hesitant on buying the PS5 now or waiting for the PS5 Pro to come to the market. His talk is The Two Faces of Cancer, Janus Kinase-Induced Identity Change.
Okay. Janus is a god from ancient Roman myth. He's usually depicted as having two faces. Like Janus, cancers also have two faces. One is sensitive to the drugs, while the other one is resistant. In my research, I found that Janus kinase is responsible for the change of cancer identities. And why is that important? The fight against cancer is almost as long as our own history. To date, we have made great progress and significantly increased the survival of cancer patients. However, cancer is cunning. While we keep developing new drugs, cancer also keeps evolving. To study this evolution and to find new weapons against them, our lab found a great model, prostate cancer. Prostate cancer is one of the most common cancers around the world. 6 out of 10 elderly American men are diagnosed with prostate cancer. And again, like the Janus, prostate cancer has two faces, drug-sensitive and drug-resistant. For the drug-sensitive cancer, it is composed mostly by one single type of cells. So scientists design drugs to specifically kill this type of cells while leaving the other cells alone. Unfortunately, cancers see through that. Under the strong pressure of distinction, cancers harness Janus kinase to change their identity from one single cell type to multiple different types of cells. Since the drug only killed that one type of cancer, cancer used this new resistant identity to escape and continue to grow. So, how do we treat this new resistant type of cancer? In our studies, we found an inhibitor that suppresses Janus kinase activity. Once we apply this inhibitor to cancers with resistant identity, they will change back to the sensitive identity. This indicates that Janus kinase is the master regulator of this identity change, and also that this identity change is reversible. And in combination with drugs targeting sensitive cancers, we can kill them again. Now we are trying to answer more questions, like how Janus kinase actually induce this identity change, and whether the combination of drugs and inhibitors can benefit the real-world patients. So in conclusion, both the god Janus and cancers have two faces. Janus kinase induce cancer's identity change from drug-sensitive to drug-resistant. And inhibiting Janus kinase can reverse this progress and may benefit the real-world patients. Thank you.
All right, thank you so much for that. Now we're going to have Natalie Bell. Natalie is a second-year biomedical engineering student in the Advanced Neuroscience Imaging Research Lab. In addition to her PhD work, Natalie has been planning her fall wedding, serves as president of the Biomedical Engineering Society, and is a proud mother of 2 pugs. She will now present her talk, Preventing Punch-Drunk Syndrome.
Can I just start whenever? Okay. Have you ever hit your head on a cabinet door? I definitely have. But I bet you didn't really think about what kind of symptoms that you may or may not have. If you don't have the symptoms of a concussion, like dizziness or nausea, you probably just had a subconcussive head impact. During a season of football, players can experience over 500 subconcussive head impacts in a single season, which is why many researchers now believe that concussions as well as subconcussive head impacts could contribute to neurodegenerative disease development like punch-drunk syndrome or chronic traumatic encephalopathy, as they say in the medical field. However, many research studies have been focusing on NFL and college-level football players and not a youth group, which is why my research aims to investigate neuronal functional brain changes in a 8 to 13 age group across a single season of football when exposed to multiple subconcussive head impacts. We measured subconcussive head impacts by using sensor-embedded helmets that then were used to calculate risk-weighted cumulative exposure, or RWE. We then measured our functional neuroimaging metrics by using something called magnetoencephalography, or MEG. MEG is used to measure brain activity or brain waves directly by measuring thousands of magnetic fields produced by neurons. Now, the slowest brain waves are typically increased during the deep sleep, but whenever a person's awake and we see these waves increase, that usually indicates that there's some kind of brain injury going on. So what I did was use MEG and RWE to conduct a regression analysis to compare head impacts to our brain changes. What I found was that as head impacts were increasing, we also saw that our slowest brain waves were also increasing in our football group, which is abnormal for this age group. Now, this research might sound alarming, but we're not here to cancel football. I love football. What we're really here to do is propose a hit count, similarly to what they have in baseball, which is a pitch count, to kind of bench players after a certain amount of head impact exposure has been felt for that season, and that would essentially prevent punch-drunk syndrome from occurring. A pitch count in baseball was originally implemented to prevent long-term use of the arm to get damaged, and so that is what we're trying to do with our football players. Thank you so much, and yeah.
I'm going to take a mini breather here while our judges are finishing up some of their forms. And I'd just like to thank the PIs and the postdocs who helped us with round one of this competition. So we had 12 students submit talks earlier in August, and then we had the following judges who helped us judge those and then narrow it down to the final 8 that you're seeing today. So we've got Dr. Kate O'Donnell, Dr. Lou Sun, Dr. Peter Lee, Dr. Samrapita Sengupta, Dr. Ramona Durrow, Dr. Dustin Hanks, Dr. Natalie Lundstein, and Dr. Lisa Dennison. And then this year we also had 3 postdocs help, Dr. Razia Sultana, Dr. Andrea Pena, and Dr. Daniel Gendon. So if we just give a round of applause to all of these PIs and postdocs. Without them, we couldn't have gotten to this stage of the competition. So I'm going to hand it off to Alexis to introduce our next speaker.
Awesome. Okay, back to the talks. Now we have Michaela Stokes. She is a 5th-year GD&D student in Dr. Lee Krause's lab. Michaela told us that she grew up on a small island in southeast Alaska. Her talk is a new regulatory component of fat cell development.
Okay, so obesity is increasing more and more all the time. It's actually projected that in America, more than half of Americans are going to be obese by 2030. And this is really important because obesity actually increases the risk of a number of other diseases, including diabetes, cardiovascular disease, even reproductive diseases and disorders. And in total, it's estimated that obesity costs the US healthcare system $190 billion a year, making it really important that we try to understand obesity and how it's contributing to these diseases. So when we're taking in more energy than we're burning, we have to store it somehow, and we store it in the form of fat. And there's two ways we can do this. We can take the fat cells that we have and make them a little bit bigger, or we can signal to these pre-fat cells that we have stored away, and we can say, hey, we need you, develop into a mature fat cell. And when this happens, those cells are able to kind of share the load or share the burden, and they function very efficiently, making it really important that we try to understand what regulates going from these pre-fat cells to these mature fat cells. And if you think about it, they're two totally different cell types. They have totally different functions, and they have different machinery that allows them to perform those functions. And so one way that we can regulate changes like this in a cell is through transcription factors, these proteins that go and bind to DNA at very specific locations, and they turn on very specific sets of genes. And so throughout fat cell development, CBP beta is known as the pioneering transcription factor. It's the first one to turn on. It binds to the promoter of PPAR gamma, and through doing this, it turns on a cascade of all of these genes that these cells need in order to perform that function as a mature fat cell. So I found through screening various other proteins that PARP7 was required for fat cell development. If you don't have PARP7, your fat cells are unable to develop into mature fat cells. And so in asking why, I did a number of experiments that showed that PARP7 is actually binding to CBP beta, this pioneering transcription factor. And not only are these proteins bound together, but these proteins are found together at the location of PPAR gamma's promoter. When this happens, PPAR gamma is able to turn on, and subsequently all the other genes turn on as well, allowing these cells to build the machinery that allows them to become these mature fat cells. When we don't have PARP7, we no longer see CBP beta able to bind to the promoter of PPAR gamma. And consequently, we don't see any of these genes turn on. We don't see these cells able to build the machinery that would allow them to function as a mature fat cell, and they're stuck in this pre-fat cell state. And we think this is really exciting because this is the first time we've shown PARP7 playing a role in the development of fat cells. And not only is it this new regulatory component of fat cell development, but we think that through understanding these components of fat cell development, we can better understand how our fat tissue works, how it's regulated, how it's then dysregulated during obesity, how that contributes to these various other diseases. And hopefully through finding these specific mechanisms, we can find ways in which we can combat these effects of obesity on these other diseases and try to save the healthcare system that $190 billion a year.
All right, thank you so much. That was great. I once again want to thank the audience for being here today, and I would like to remind everyone that at the end, we're going to have the audience vote on their favorite talk of the day, because that person will also be winning a prize. So please stick around after the talks are done to help vote for the audience favorite. Next up, we have Pega Ascari, who is a third-year biomedical engineering student who is also in the Advanced Neuroscience Imaging Research Lab. And her talk is entitled Towards Automatic Labeling and Processing of Clinical MEG.
We have an amazing brain. Our brain is a piece of art. It does so many wonderful things. But sometimes it just doesn't work as we would like it to work. In people living with epilepsy, the neuron can experience a sudden burst of intense electrical activity, causing recurrent and spontaneous seizure. Epilepsy affects more than 50 million individuals worldwide, and even with the great progress in science, there are still 30% of patients who do not respond to medication, and they need surgery to remove the part of the brain that's causing the epilepsy. So it is important to correctly find the location of this epileptogenic zones while also saving the functional area of the brain for a successful surgery outcome. and the, so, sorry. So it is important to find the correct location. So one of the important biomarkers to correctly find the epileptogenic zone is the spikes, and this spikes can be measured with the magnetoencephalography known as MEG. MEG is a non-invasive imaging technique that can measure the magnetic fields induced by electric currents in the brain. The spike detection is done by visually scanning the MEG signals by a trained neurophysiologist. And this spike detection is manually possible, but it's like finding a needle in a haystack, and it's a subjective method. So in my research, my goal is to develop an machine learning algorithm that will be able to detect and automatically the spikes, to automatically detect the spikes to make this process and the clinical practices more automatic and efficiently. So my code takes the clinical resting state MEG signal as an input, and then will provide us with the output, which is the spike time points. Then we are using the clinical resting state MEG signals for as an input to our machine learning, and then we train our network based on that to detect and predict the labels for the spikes. So we know that the reading the MEG signals and finding the spikes could be a time-consuming and laborious task, but I'm excited about the prospect of my research that would be able to help us in the future to do this process more automatically and efficiently. Thank you.
Thank you, Pega. Now we have Bobby Pendry, a fourth-year neuroscience student in Dr. Brad Pfeiffer's lab. Bobby enjoys spending time with his various cats and houseplants, and his talk is titled Monitoring Brain Development in Real Time.
So, if I asked you to recall your earliest memory, what would come to mind? Maybe riding in the car with your parents, sitting in a car seat at like the age of 3, or seeing the family dog through the bars of your crib at the age of 2. It's probably something vague, only a fuzzy memory. Whereas if I asked you to recall a really memorable childhood experience, you'd probably be able to conjure every last detail about that time you fell out of a tree and broke your arm at the age of 10. Certain memories crystallize better than others, especially novel, emotional, painful ones. But on the whole, as we grow older, we get better at learning and remembering things. Now, when this process goes awry, it can result in intellectual disabilities that take hold in childhood and usually linger on into adulthood. Studying how exactly that happens is really challenging. A lot of scientific research is off limits for humans, especially human children. So my research in this area involves using mouse children, which might sound really odd because mice are so unlike humans in so many ways. They're small and furry, and they don't live as long as we do. But their brains develop a lot like ours do. And they behave like us in fundamental ways. And above all, they are resilient like we are. And that last part is important because studying deep brain activity in mice involves this rather invasive process of sticking wires into the brain, surgically attaching a device that holds the wires in place, and then plugging that device into a computer. If done properly in adult mice, those wires can monitor electrical activity in those deep brain areas while the mouse is able to run around and freely behave. Now, doing this in tiny little infant mouse pups has a lot more challenges. Most notably, they're simply too small to bear the size and weight of the device and still do normal things like eat, drink, and play. And so it's long been thought that this is impossible or impractical to do these experiments in tiny little juvenile mouse pups. Until now, I've refined the size, weight, and surgical process of implanting these devices in infant mouse pups, something that's never been done before in neuroscience. And so we can, for the first time ever, monitor this activity. This breakthrough allows us insight, unprecedented insight, into how the brain develops in real time in mouse pups as young as 19 days of age, which is the equivalent of a 2-year-old human child. And so now, for the first time ever, we can monitor the development of the brain in real time from infancy all the way to adulthood. And doing this in normal mouse pups, wild-type mouse pups, comparing them to ones that are genetically predisposed to an intellectual disability, we observe subtle differences in how their brains crystallize brand new memories. And these subtle differences can go a long way towards explaining things like how children with autism remember certain things extraordinarily well, but aren't so good at learning and remembering other things. And my research brings us a lot closer to understanding how and why that is. Thank you.
All right, thank you so much. All right, second last, we've got Shrujani Biswas. She is a neuroscience student in Dr. Steve Shabel's lab. She says she loves books and beaches and could see herself becoming a beach town librarian someday. Her talk is entitled Modeling Pessimism in Mice.
Imagine you've been hiking for an hour and you reach a crossroad. You can choose between the path on your right, where you see a sign for water and restrooms in a mile, or you can choose the path on your left, where you see potholes and poison ivy on the sides. Chances are you'll choose the path on the right because it looks safer and more comfortable. But what if someone was predisposed to think that both paths are dangerous, even if there was no reason apparent to believe that? This could increase their chances of choosing the more dangerous road, or they could be stressed out even as they took the safer road, and long-term stress can also be dangerous. This excessive expectation of negative outcomes in good, bad, and neutral situations can be termed as pessimism. Over time, persistent pessimism can affect one's cognition, which in turn can affect quality of life. Incidentally, pessimism is common in people with depression, OCD, and sleep disorders. The goal of my thesis is to provide one piece of the puzzle in understanding what might be happening in the brain during pessimistic behavior. And to do that, I'm modeling pessimism in mice. Mice are actually great model organisms for studying the brain because the mouse brain is organized much like the human brain. And there are many tools to study very specific parts of the mouse brain, which is not as easy to do in the human brain. So, how do I model pessimism in mice? I place mice in a controlled environment where I have programmed certain tasks for them. They can get good, bad, and neutral situations, and I want to see how they react to these very different outcomes. I'm watching and comparing the behavior between two types of mice. One that has a normal genetic background, and two that has features of depression. I expect to see that the mouse model of depression will be more pessimistic than the other model. That is, these mice will behave as if they're getting the bad outcome in all of the different situations. I'm also recording brain activity to see how the brain activity might be different between these two models of mice. Preliminary results show me that some brain regions that are important in encoding rewards and punishments are more active in the mouse model of depression. With these experiments, my hope is that with a better understanding of what's happening in the brain during pessimism, we will be one step closer to understanding and easing this debilitating behavior. That way, more people can hike through life in a stress-free, injury-free manner. Thank you.
Awesome. We've had so many great talks so far, and we're on to our very last one of the day. So, last but not least, we have Sebastian Fonseca. He is a fourth-year biomedical engineering student in Dr. Madhurantikam's lab. Sebastian loves cooking, and he says he makes the tastiest boiled water with burnt toast. His title of his talk is Using Tumor Density to Improve Cancer Diagnosis Accuracy.
It's 5 p.m. and you're racing to make it in time for happy hour at your favorite restaurant, but you're stuck on bumper-to-bumper traffic on the highway. Every single lane is backed up by cars just trying to get through, honking. Not the most beautiful picture, I know. Now picture this. It's a quiet Sunday morning in the middle of quarantine. There are no cars on the highway, and you've never been happier in your life, right? Well, these two scenarios resemble quite well the differences in cell density between tumor tissue and healthy tissue. You see, tumors are often denser than the healthy tissue surrounding them. And because of this, water molecules cannot move as freely, in the same way a car cannot move in a traffic jam. In such images, regions with high cell density or cellularity will appear bright, whereas regions with lower cellularity will appear dark. Diffusion-weighted images are widely used in radiology because they provide great contrast between cancerous lesions and healthy tissue. And however, there are two main drawbacks of using diffusion weighting. The first one is motion. I don't know if any of you have ever been in an MRI, but one thing they always tell you is to stay as still as possible because motion can cause distortions in the image, which are accentuated whenever diffusion weighting is applied. And let me tell you, it is very difficult to stay still like this for like 30 to 45 minutes at a time. And it's even harder for certain patient populations like children or the elderly. The second drawback is that fat tissue can sometimes be confused with tumor tissue because fat is also very dense and will thus also appear very bright in diffusion-weighted images. Going back to our car and traffic analogy, it's like if the vehicles and the roads were the exact same color. Looking down from a tall building, it would be very difficult to differentiate the cars from the asphalt. And sometimes physicians have a really hard time outlining the margins of the tumor and can even make mistakes by identifying fat tissue as tumor tissue. My project is focused on addressing these two issues by designing a novel data acquisition strategy that oversamples certain parts of the image at specific time intervals and uses this additional data to correct for motion-induced errors. Additionally, with our strategy, we are also able to single out the signal contributions from fat and null it to effectively create fat-free images. If our project becomes successful in patients, it has the potential of improving the accuracy, the diagnostic accuracy of MRI, and therefore can improve patient outcomes, better tailored treatment plans for patients, and increase overall survival rates. Thank you.
Thank you. Amazing talks today. So we have right there the QR code for our People's Choice. Everybody please grab your phones out and vote. We will be giving away a first prize of $600 to the winner. We have a second prize of $400, third is $200, and then our People's Choice gets $100. So we'll give you 3 to 5 minutes to vote. And in the meantime, we are going to have Veronica from GSO come up and talk a little bit.
Thank you, Alexis. Hi, my name is Veronica, and I'm International Student Representative of GSO. And today I'm representing GSO in general. First of all, I would like to thank Lexus and Pri for organizing this amazing contest, and all you guys, you done great. And now I just want to quickly talk to you about GSO. Most of you here are the grad students. And please remember that we all struggle through the same situations most of our PhD career. We are here to help you. We are here to support you. We are here to advocate for you if you have any issues. We are here to help you socialize together. We have a lot of social events coming from the GSO. Plus, every second Tuesday of the month, we have a GSO meeting, which I encourage all of you to come. There is free pizza always. And if you have any issues that you want to talk about, that maybe you are afraid to tell to your PI or to the dean or to whoever, you can always come to us, to GSO, contact us, and we'll help you or support you whenever you can. Thank you.
All right, so I'm going to announce audience favorite right now. We had 48 votes, which is amazing because we really had no clue what the turnout would be since we were across campus, and so we're really happy that we had almost 50 people here to vote. And so what we have for the winner of the audience favorite is Shivani Biswas. There you go. Oh, you will get the money in your stipend check. Yeah. And it's just a bonus on your paycheck. Ready? Okay.
All right, we have our 3 winners. So our third place finalist is Michaela Stokes. Congratulations. Yeah, if you just stay up here. All right, our runner-up, second place, goes to Therese. Well done. And our winner is the same as our audience favorite, Shrujani. Congratulations. All right, so let's take a picture.
Cool, congratulations.
Yeah. All right. Well, thanks so much, guys. Thanks for coming to this year's competition. We hope to keep doing this every year with the grad school. It's proving to be very popular. So feel free to hang out afterwards, go to Community Brewing, get a beer or something, and hang out with your lab mates and friends. And we'll hopefully see you next year.